Cool, that all looks good. All right, so hello everyone. It's nice to see you for another AFMS seminar. So it's my pleasure to introduce our speaker for today, Dr. Dan Lucas, who is a lecturer in applied mathematics at Keele University. So Dan received his PhD from the University of St Andrews under the supervision of Professor David Dritchell. And since then, Dan has held positions in Bristol, the University College Dublin, and most recently in Cambridge, working with Kolmogorov and Chandler Kerswell. And so Dan has a keen interest, I think it's fair to say, in using novel numerical approaches to shed light on the fundamentals of turbulence and exact coherent structures. And he's going to be talking about some of that work today. So take it away, Dan.
Wonderful. Thanks, Kat. Thanks for the invitation to talk as well. And I think as well, I understand that the time has been pulled forward an hour to make it less antisocial for me. So that's very much appreciated. I have to confess to not being much of a morning person, so I do apologize if there's more ums and ahs than there would normally be. So anyway, this talk is the first kind of set of results coming out of my EPSRC new investigator grant, which has funded my postdoc at CU Suda to come and work with me as well. And we're at Keele University in the UK. So if you don't know where Keele is, it's just outside of a city called Stoke-on-Trent, which is halfway between Manchester and Birmingham. So we're out in the sticks, and it's a beautiful kind of countryside campus. So anyway, on with the science. So what I'm interested in is trying to understand and describe in some way turbulence. And I'm showing you here a movie of transitional plane coet flow, so the flow between two anti-parallel moving plates in quite a large domain. And what you can see here is lots of complicated behavior in space and time. So you see disordered motions at various length scales, and you see chaotic motions as well. So this makes it a very challenging problem to describe mathematically, and also to make predictions about over long times. So this is probably not a surprise to you, but our approach is, say, atypical in some respects. And what we attempt to do is use a kind of so-called dynamical systems approach to unpick some order from that chaotic and turbulent mess. So there's a series of plots I'm going to show you now to kind of exemplify what the approach is about. So here I'm plotting a turbulent trajectory on a plane, which is the energy inputs into the system and the energy dissipation in the system. And as time evolves, in this projection, you map out this chaotic tangle, this mess of turbulence, and it seems very hard to pick out any order from plots like this. However, if you look carefully, every so often you will notice that there are these episodes which seem to almost, but not quite, repeat or recur. So in this solid black curve, the trajectory nearly closes on itself. And of course, this is a projection of a very high dimensional dynamical system. So if you think about your direct numerical simulation having hundreds of thousands, if not millions of degrees of freedom, this is a projection down onto 2 degrees of freedom. So you need to always have that in mind, but even still in this projection, it seems like the trajectory nearly closes. And what we consider the possibility of is that this is a close approach or a shadowing of an underlying unstable periodic orbit embedded in that chaotic attractor. And here is one such orbit that the black curve is shadowing. And this has been picked out with some numerical method, which I'll describe in a bit more detail later. But the point is, once you have these underlying periodic orbits, you can use them as proxies for the underlying turbulence. So here's what these flows look like. So one of these is the black turbulence, direct numerical simulation of the turbulence. And then the other movie is the underlying unstable periodic orbit. And hopefully you can see, I deliberately haven't labeled which is which, to try to get you to use your eyes and see if you can see how much difference you can spot between them. And actually there isn't, I would argue, not that much difference. So you can see then how useful these can be as proxies for the turbulence. Because they're a closed loop of process, you can unpick what's sustaining the turbulence from them, and they can be some reduced order expression of all that complexity if you can find a few of them. So that actually these orbits in particular will work with Column on stratified turbulence. This approach goes back, really has its roots in some work by Kawahara and Kida in 2001. And they were really the inspiration for a lot of what's happened since. And they were able to show these two periodic orbits embedded in plane wet flow turbulence. So again, you see a similar plot on the left with a recurrent episode shown, I think, in the yellow curve, and the red curve showing the converged unstable orbit. And what they showed was that one orbit in isolation was actually a very good proxy for the average measures of the flow. So for example, mean velocity, RMS velocity, the orbits are shown in the symbols, and then the solid curves underneath are the actual turbulent averages. So given one orbit is such a good proxy of these sorts of measures, that this was sort of the motivation then to go ahead and try to see how robust this result is and how generalizable it is. The other thing I want to mention quickly is in the title of my talk, I use the phrase exact coherent structures. So that includes unstable periodic orbits, but it also includes structures like equilibria and traveling wave solutions. So typically we're thinking of them as nonlinear solutions that exist embedded in the turbulence in the same way, but instead of being time dependent, they are steady or traveling with some fixed speed. So here are just some examples in different flow geometries. So channel flow, a traveling wave, and a traveling wave in pipe flow as well. So just to kind of be definitive, what I'm talking about by exact coherent structures are the whole set of equilibria, traveling waves, periodic orbits, and also periodic orbits themselves can travel, as we might discuss a little later, and be relative periodic orbits if you have a continuous symmetry in your system. So moving on from Kawahara and Kida, then probably the next, I would say, benchmark result in this area was in 2013 when Rich Kerswell and Gary Chandler published this paper where they kind of show how you can extract on these unstable periodic orbits in some abundance. So they were finding in this two-dimensional Kolmogorov flow, which again I'll talk about in a second, orbits at certain Reynolds numbers at the kind of order of 50 or 200 orbits in one kind of set of results. And in this way, then you can really start to use them as an expansion for your turbulent flow, and you can consider how you best add them up and weight them in some way to kind of give you a reduced order description. So what they did was something called the recurrent flow analysis, which really was what I showed in the first few slides with the close shadowing and so on. So basically what you do is you perform a direct numerical simulation of your turbulence, you store some history, and every so often you go back through the history and you look for an episode where you nearly recur. So that black curve I showed on the plot earlier. And those end up being output and used as guesses for a second algorithm, which is this so-called Newton-GMRS hook step, which seeks to solve exactly the condition you see here, so where omega is the state vector of your system, that omega at some later time capital T minus the starting omega is equal to 0. So this will be the exact recurrence. So the picture you have in your head is this little cartoon on the right where coming from the DNS is some close approach to being recurrent, where there's some residual left over between T and T minus capital T or T plus capital, whichever way around you want to think about it. And the goal of Newton-GMRS is to close that gap such that it's 0 to machine precision. And the way that that happens is using this Newton-GMRS hook step algorithm, as I say. And one step of the Newton method is kind of encapsulated in this linear system below. However, what you need to bear in mind is the Jacobian on the left-hand side here requires variations of the end of the trajectory with respect to the beginning of the trajectory. So that's, don't forget this term on the left of the recurrence condition requires the solution of the full nonlinear Navier-Stokes equation. So not only is this matrix enormous, but you also can't write it down. So that's where GMRS comes in as a matrix-free method to enable us to solve the Newton step. And then the hook step part is simply to constrain the trust region of your Newton step such that you're always in that linearized region of a Newton step. And this method works pretty well, as I described for Chandler and Kerswell, and you saw some results using the method to look at stratified turbulence earlier on. However, when you push to high Reynolds number and more realistic system sizes, it becomes very hard to find good guesses for your Newton GMRS method. So in other words, close approaches or close recurrences aren't so easy to find, primarily because the unstable orbits are becoming more unstable, and therefore you're not shadowing them as thoroughly as you need to be able to pick out a recurrence. They're more kind of fleeting episodes. So a lot of current trends in this area are trying to find alternatives to either the recurrent flow analysis altogether, or simply better ways to find guesses. So people are looking at things like Koopman DMD and machine learning and various other variational approaches to finding these exact coherent structures embedded in turbulence. But I'm going to take a slightly different tack. I'm going to see if I can find ways to stabilize my exact coherent structures. So the method I'm going to look at is this one going back to Pyrgas in 1992, and it's one where you add into your dynamical system this blue term, which is a time delay term. So you take your state vector at the current time and you subtract the state vector at some delayed time, delayed by a period capital T. And it can be shown in some circumstances this will stabilize periodic orbits at periods capital T. And the really nice thing from our perspective about this is that it's so-called non-invasive. If you stabilize an orbit of periods capital T, then this term vanishes, and therefore you have to be sitting on a solution which exists in the uncontrolled system. So if you can make this work for Navier-Stokes equations, you're actually picking out solutions of the Navier-Stokes equations, even though you're adding in this extra control term. So then the game comes down to finding gain matrices G, which allow this stabilisation to happen. Now, if you haven't heard of this method or this approach before, it's potentially because of this so-called odd number limitation, which has been a kind of contentious issue for this work and potentially been holding it back somewhat. So there's been a whole raft of papers discussing and describing this limitation, trying to find workarounds to it, and also finding kind of counterexamples of it. I mean, I've just put up a selection of the papers here, but there's really quite a big literature on this now. But I'll just try and describe to you what the issue is. It's basically if your orbit has a purely real Floquet exponent, then the method is expected to fail. So this plot I'm showing on the left-hand side is an eigenvalue spectrum for a solution that we're going to talk about later in the talk. But the important thing is that the blue dots are the spectrum without any time delay feedback. And what you can see to the right of the real axis, there are 5 unstable eigenvalues, 2 complex conjugate pairs, and there's one sitting on the real axis. If you just naively employ a time delayed feedback control method to try to stabilize this solution, what you find is you can stabilize the complex eigenvalues. So these 2 come across the real axis and are stabilized, but the ones sitting on the imaginary axis, the ones which are purely real, are actually amplified. So you make these eigenvalues more unstable. And this kind of exemplifies in some way this odd number limitation. And as I say, there are a number of ways and methods purported in the literature that might circumvent this issue. So for example, in this case, they employ some complex gain to kind of rotate your spectrum somehow. But it's obviously something we're going to have to be mindful of doing the high dimensional Navier-Stokes case, where certainly at high Reynolds number, you're expecting to have very high dimensional unstable manifolds, and the likelihood is you're going to pick up eigenvalues which are purely real. And as I said, this is probably the reason why we haven't seen it used to great effect in fluid mechanics. So there are a couple of examples in my literature search I've been able to find. One of them goes back to Kawahara in 2005. And it's a kind of side note in this paper on transition in plane co-wet flow, where he stabilizes this UPO sitting on the edge of turbulence. And the result is kind of nice, but it's understated in the paper and it's not really explained. The implementation isn't really explained. And also there isn't much detail given, basically. And the orbit is shown stabilized for a few periods only. So it's not really clear why Genta didn't keep working on this if he got put off by the odd number limitation or some other reason. But it was kind of a passing result in this paper. And there was another paper where they used time delayed feedback in an experimental study of Taylor co-wet flow, so the flow between the annual gap between two cylinders. And I would say there in an experiment, the ability you have to apply this method is slightly different, and also the kind of motivation for doing it is maybe slightly different too. So here they're really just interested in controlling chaos in some way. I think they're slightly less interested in trying to find exact coherent structures. But anyway, they're successful. They're able to use the method. Excuse me. But certainly, perhaps not in the same spirit that I'm proposing to use it for. So anyway, I should crack on with my results and the system I'm interested in. So I'm going to study 2D Kolmogorov flow, which is the one that Chandler and Kerswell studied and has been studied quite widely for this type of thing in recent years. So basically it's a 2D Navier-Stokes flow with a sinusoidal body force, non-dimensionalized, such that you have a Reynolds number appearing as your only control parameter. I'm considering square domains. I'm considering the now classical n=4, so 4 forcing wavelengths in your domain. At low Reynolds number, then you have a balance between dissipation and forcing, and you have the Laminar solution appearing, which just mimics the forcing. So you're seeing vorticity at Reynolds number 40 for that Laminar solution. And it has a linear instability here at around 10, and therefore thereafter a supercritical transition to turbulence. More on that in a second. One important point for our work, which is going to be referred to a few times, are the symmetries that this system has. So solutions are invariant under the following operations. You can do a shift and reflect symmetry operation. So you shift a half wavelength in the forcing and reflect, and the solutions are invariant. You can rotate it in pi, and you can also shift any amount L in X. So there's a continuous translational symmetry in X. So you can do all these operations to a solution, and it will still be a solution of your system. And these are very important for finding exact coherent structures, particularly the continuous one, as that allows for traveling waves in relative periodic orbits. So we'll talk more about that as we go through. Just for context, here's a realization of Kolmogorov flow with these flow parameters at Reynolds number 200. And you see kind of fairly classical 2D turbulence, kind of vortex merging and filamentation and so on. So that's just to give you some context. So I should also say we're solving for the direct numerical simulation, solving using a pseudospectral method, pretty standard method, but implemented on GPUs. So we have a very fast and efficient time stepper. Okay, so I'm going to add in this time delayed feedback forcing to the right hand side. I'm going to do it to the vorticity equation because that's the efficient variable to use for the DNS. But I'm going to use the stream function to implement the force, this time delayed forcing. Now that's for a couple of reasons. One, it makes the linear stability analysis I'm going to show in a second a bit cleaner, but also has the effect of weighting the large scales a little more than vorticity would. So it turns out to be advantageous from that point of view as well. And really, there isn't much of a trick here because the gain matrix can be almost anything. It could also be the inverse Laplacian. So I could have left vorticity here and just had the gain matrix encode the inverse Laplacian in Fourier, and it would be equivalent. So there's nothing really fancy going on here. I'm just trying to be as transparent as I can. You'll also notice that I'm leaving in a translation in X for precisely the reason I just described. This will allow me to hopefully stabilize traveling waves and relatively traveling periodic orbits as well. Okay, so the first thing I'm going to do is kind of validate the method and make sure that I understand what's going on to some extent by doing a linear stability analysis of the base flow, including in there my time delay terms. So it's basically a repeat of what's been done lots of times before. My base solution is the laminar one I showed you earlier, just mimicking the forcing. So I have a parallel shear flow. I plug in, I linearize my equations. I use the usual ansatz. So I have a streamwise wave number alpha. I have a complex growth rate sigma. And I have eventually this kind of modified version of the Orr-Sommerfeld equation to deal with. Now, the important thing here is that normally the sigma appearing on the left-hand side is nice and linear, and everything is easy to solve numerically to get your eigenvalues. However, in the case where you have the time delay term, you have this exponential involving sigma t. So this makes the linear problem now transcendental in sigma. So I'm just moving on this slide, but the same equation appearing. So this makes it a little bit of a problem, but what I'm going to do is assume that the combination sigma t is small, and I'm going to do this by basically ensuring that my capital T is small. So my time delay is small, which is an appropriate thing to do if you think about it, because I'm trying to stabilize a steady solution. I don't have a specific period for this solution in mind. I just want to stabilize a steady solution. So some small capital T is kind of an appropriate and possible thing to do. So then I expand my exponential to linear terms in sigma, and I can make headway. And you notice that I've left in the translation in X. So the S appearing here is the shift in X for good reason, which I'll come back to, but you can already see if you set S equal to 0 here, this term vanishes. So it has a reasonable consequence on your stability problem. So here is essentially, this is the unstable spectrum I showed you earlier. So it's for the laminar flow at Reynolds number 40, so well above criticality. And at this Reynolds number, so first of all, the primary instability is a pitchfork bifurcation, so that's giving you the purely real eigenvalue sitting here. And at this kind of relatively high Reynolds number compared to the critical one, you've also developed these two complex conjugate pairs of eigenvalues as well. And as I showed you earlier on, simply putting a large gain here it can stabilize the complex eigenvalues, but it actually amplifies the real ones. And this is actually with the shift equal to 0. So this is where you can probably guess what's going to happen next. If I include a shift, then what happens is you kind of rotate the spectrum and you lift the eigenvalue sitting on the axis off the axis. And you continue increasing the shift, and then the whole spectrum can be swung around into the left-hand side, and you've managed to stabilize the solution at relatively modest amounts of gain compared to the 2000 that I showed you that you needed to go to stabilize without the shift, even those complex eigenvalues. So in summary, then it's possible to use this method with an appropriate translation in X to stabilize the laminar flow. So to flesh out the situation in a bit more detail, I'm plotting neutral curves for different Reynolds numbers here, for different gains along the x-axis and different shifts on the y-axis. And you can see that obviously, unsurprisingly, for higher Reynolds number, you need progressively higher gains. And then you have these gaps in your stabilisation. So maybe I didn't mention as well. So stabilisation is to the right of these neutral curves. So where you see around 2, this gap is where the stabilisation fails. And I think I'm coming back to that in a second. But before I do that, I can show you the DNS agreeing with the theory. So this is for Reynolds number 40, shift of 1. ordinarily quite turbulent and disordered. This was the same Reynolds number that Chandler and Kerswell did a lot of work on, and you can see stabilisation quite quickly. So going back to these gaps, up to Reynolds number 200 was essentially as far as I bothered to go. There are 3 unstable streamwise wave numbers, and these gaps correspond to the places where those the shift times the corresponding alpha is equal to 2 pi, and therefore that term on the right hand side of the Sommerfeld type equation vanishes. So these gaps are where this term is vanishing. So it's almost like the effect of the shift disappears at these places. So in particular, this gap here that looks around 2 is actually 2 pi over 3 due to the alpha equal 3 streamwise wavelength being unstable at these Reynolds numbers. And actually you can see this in a direct numerical simulation. So I do the same case I showed you before, but now do s equal to 2. And the stabilisation fails, but more interestingly, it ends up giving you a very distinct streamwise mode 3 pattern. So you see precisely the feature of the failure of stabilisation appearing. So essentially, streamwise wave numbers 1 and 2 are fine and they are stabilised, but the wave number 3 is very obvious in the DNS, which is maybe slightly surprising given that the flow looks very sort of nonlinear, and maybe not disordered as such, but definitely nonlinear. Okay, so then you can obviously go to more detail and look at things like the overall size of the delay term. So this is some measure Q, I'm going to call it the residual. So in some L2 norm, a relative measure of the size of the delay term. And you can also sort of define distances to the laminar. So here it's just how far off is the energy input from its laminar value. Down on the bottom left, I'm showing Reynolds number 40, gain of 20. And the important one, you can see Q basically dropping off and going to 0. And the important ones to look at are the two down here, the blue and the yellowy colored ones. So this is really showing you how precisely I can match the location of a neutral curve in the DNS. So the neutral curve sits bang on 1.5 more or less. And you can see that the kind of yellow one begins to stabilize and then realizes it's actually unstable, picks up the unstable manifold and goes elsewhere, whereas the blue one stays stable. So really you can pinpoint the neutral curves quite precisely. And then on the other side, then Reynolds number 200, quite high Reynolds number. So that was the same Reynolds number of the very first video I showed you of the flow. Again, choosing the right shifts enables you to get stabilization, and a badly chosen shift fails. Okay, so that was all kind of preamble, because really what I'm interested in is finding these nonlinear unstable solutions rather than simply stabilizing the laminar, but it has given us a bit of a feel for what's going on, and we've learned a little bit along the way. What I want to do now is try to tackle these traveling wave solutions. So here's a traveling wave in this flow. So this was reported by Chandler and Kerswell. And obviously here you now have this connection between the translation index and the delay period that you set. So this combination has to reflect the phase speed of your traveling wave. So you now don't have the ability to set whatever S you want, but it has to match the phase speed of your traveling wave. Also, I should point out that this traveling wave here at Reynolds number 100 has an unstable spectrum which is made up entirely of complex eigenvalues. So this should be a really good candidate for testing our method on it. It should not have this odd number limitation that I was discussing earlier. I should also say that we want to work on the assumption that we don't know anything about the traveling wave in advance. A lot of the implementations of these methods know something about the periodic orbit before they start. So they know the period and they know roughly where it is in phase space perhaps. But we want to work on the assumption that we don't know anything at all about these solutions and try to organically stabilize them And in doing so, especially in these traveling wave cases, what we want to do is find the phase speed as part of the problem. So the way that we do that is actually, so we set a delay period capital T, and then we try to converge or adaptively find the shift corresponding to the phase speed of the traveling wave. So the way we do this, it was with a simple descent method. So we solve this ODE, where this delta S is the kind of, if you like, the gradient with respect to the delay term of the shift. So the way I define it is as an average of essentially the Fourier phase rotations. So each Fourier component in the state vector, the shift of it amounts to a rotation of its phase. So you look for essentially the average phase rotation modulo the division by kx to give you an estimate of the shifts for each mode, and then create some average of that. This is actually a bit of a ticklish operation because you need to be careful about what branches of this argument function you lie on. So if you're using complex log or an arctan to get the argument of these complex Fourier modes, you need to be mindful of what branch of that function you're on. So it takes, there's a little bit of nuance here that I don't really want to go into, but the code will be available in due course for how I do this. But basically what it amounts to is that I'm able to, on the fly, as I'm doing my time delayed feedback control, also find the phase speed of the traveling wave. So here's an example at Reynolds number 40. So I'll just play the video again. Of the stabilisation of that traveling wave, and at the same time in the yellow curve, finding the phase speed by adapting the shift, having set the period of the delay to be 0.2. And it works quite nicely, and it's in good agreement with the values which are predicted. And notice I'm starting from 0 here. So there's an open question about how good my method is for if you start off your initial shifts a very long way from the corresponding phase speed that you're looking for. But certainly a naive guess of 0 gets you the traveling speed in this case. It's ongoing work to determine how robust that is in terms of the starting value and the target traveling wave. And it works up to Reynolds number 100, as you can see here, where you're fairly turbulent. I should also point out that if you don't update the translation, then the kind of result is somehow indeterminate. So you kind of do stabilize something, but it isn't quite the traveling wave, and the residual doesn't go to 0. So here the blue curve is showing you the case without with basically just a 0 translation, so a 0 phase speed in your delay term, and the value of your Q measure saturates at some fairly large value, relatively speaking, and by adapting the shift, then you can send this Q measure to machine precision. But I suppose also probably more importantly associated with the kind of missing of the true exact coherent structure, then the energetics are slightly off as well. So this is the measure of the energy of the traveling wave, and the blue one is obviously not matching the true traveling solution in the yellow curve. So seemingly it is important that you do manage to get the traveling, particularly if you're worried about the invasiveness of your method. So really, if you want to be sure that your method is non-invasive and you're actually finding a solution of the Navier-Stokes equations, then you want Q to be vanishing, and perhaps at 10 to the minus 3 it's not quite small enough. So again, as I mentioned, you can repeat it Reynolds number 100. These are the same figures now with more curves on them. So the green one, it has the same parameters as before, so the convergence rate is much slower. but nevertheless you do get stabilisation. But at 200, no matter how hard you try, you can increase the gain, and you can try harder to find the phase speed. It seems to fail. So the red curves are all over the place. They're not stabilising, and there's a problem. And it probably won't surprise you what the problem is. As you increase Reynolds number, your unstable manifold gets higher, is increasing in dimension, and importantly, above Reynolds number 166, you have these unstable eigenvalues sitting on the imaginary axis. So these are now in violation of our odd number limitation. So that's the reason why this method is failing above Reynolds number 166. So that case at 200 is failing because of the odd number limitation again, which is, as I mentioned earlier, not surprising and something that we're going to have to be dealing with. Luckily in this case, there's a very easy way to deal with it, it turns out. So given what we discovered in the Laminar case, where you could exploit a symmetry of the underlying solution to improve the effectiveness of your time delayed feedback, it might be worth seeing if the similar thing can be done here. And actually, if you look carefully at this traveling wave solution, it might not be that obvious at first glance, but the solution does have a symmetry intact. So namely, if you take the solution, you rotate it, then you apply 3 lots of shift and reflect, and then you translate it by pi again, you get back to your original solution. So it's invariant under this symmetry operation. So it's worth trying to include this symmetry operation embedded in the time delay feedback term, and see if that has any effect on helping us avoid this odd number limitation. And I also wouldn't be telling you all this stuff if it didn't work. So here's the new version of the time delay term with the kind of shift operations shown. On the left is the case if you don't put the blue terms in. So if you don't put the additional shift, rotation, and translation symmetry in, and you can see you're very disordered still, kind of quite turbulent. And in the right-hand movie, you're seeing the stabilisation of the travelling wave. This fairly high Reynolds number, don't forget. So that's a pretty nice result. I'll just let the movie on the right play through again, just so you get a sense of what happened. Quite quickly, you end up settling onto this travelling wave solution. Okay, and I can pick up the same sorts of figures I was showing you earlier with the energy and the Q measure. So the blue one without the symmetry, again, very disordered and turbulent, and then the yellow colored one with the symmetry imposed in the feedback term showing the stabilisation. So you're probably also thinking, well, there must be other solutions in there with lots of symmetries and things intact. We're sort of in the process of trying to catalogue what you can find. We haven't kind of done an exhaustive search as such quite just yet. Here's just another example. And in fact, what you see here is the stabilisation of the equilibrium, which is the primary bifurcation from the linear stability. So this is the one with kind of essentially most symmetries intact after the laminar. So it's not surprising that by using some additional symmetries in your time delay term, you can stabilize that solution in particular. But probably not a very interesting or relevant one to the turbulence, as you can see. But interesting nonetheless that you can find it. So I began the talk by talking about unstable periodic orbits, so I should come back and say something about that before the end. Obviously, the long-term goal is finding something time-dependent and not just these traveling wave solutions, as nice as they are. So what I'm going to show you here is a kind of a sort of proof of concept study showing the stabilisation of a UPO. What you find in this flow, at Reynolds number 31, an orbit, stable periodic orbit, undergoes a subcritical Hopf bifurcation, and you get a window of chaos at Reynolds number 31. So you're seeing a trace of the dissipation rate and one of these energy input dissipation rate projections. The blue one at Reynolds 31 showing the chaos, and at Reynolds 30 showing the stable periodic orbit. So at 31, the now unstable periodic orbit has developed a complex conjugate pair of eigenvalues due to this Hopf bifurcation, and very relatively small real part. So really this should be a prime candidate for our time-delayed feedback method. The way I've been pitching this is there should be nothing easier as a test of our method than this orbit, because it's only got two very weakly unstable eigenvalues. They have complex, they have an imaginary part, so they don't suffer from this odd number limitation. So this should be kind of our starting point and our the kind of easiest thing that we can try. So here's what you do if you just try doing what I was doing before for this orbit. It looks like at the beginning you stabilize it, Q drops off, but then you can see it starts to grow again. And in fact, the time-delayed feedback method has failed. Which is surprising given what I've just said about it. This should be the easiest and most gentle test for this method. And it turns out what's happened here is that your starting point, the time at which you turn on the time-delayed feedback control, is not in the basin of attraction for your stabilized orbit. So not only do you need to worry, so the hope was that these time-delayed feedback methods would allow you just to time step onto the orbit from almost anywhere. And it would avoid you having to have good guesses, in the sense that the Newton GMRes method has to have good guesses to enable you to converge. That you can start from almost anywhere in phase space and just time step onto the orbit. That would be one of the big advantages and the big selling points of this method. However, in this case, it doesn't quite happen. And without a good kind of initial history for your feedback, this method is kind of doomed. It doesn't really work. Even if you look for a near recurrence in the way that we were showing earlier on, and switch on the gain after a near recurrence, it still doesn't really work. So the way that I've found that kind of gets around this issue is to use a kind of switching method. And what this boils down to doing is every 250 time units, turning off the time-delayed feedback to kind of refresh the history and include some new uncontrolled dynamics in your history, and thereby make sure that the invasiveness of the control method is kind of tempered, if you like, by some uncontrolled dynamics. And this is similar to this so-called act and wait method, which I'll talk about again a little later, by Pergas and Pergas. They also do this switching thing to stabilize orbits and actually avoid this odd number limitations. It's a slightly different motivation and approach, but they do a similar switching thing there. So basically I'm turning off the feedback control for 1.2 periods to do this kind of refreshing of the history. And actually this is seemingly quite effective at kind of nudging you back onto the orbit in the uncontrolled system. So again, you're seeing now a sequence of plots, one of these projections, the dissipation rates, and then the projection colored with time. So the blue one is the one I showed you earlier, where the stabilization fails. So that's where you end up. And the orange one is with the switching method turned on, and eventually you do find your way onto the orbit, and in quite short order as well, relatively speaking. You can see in the dissipation against time plot, you settle onto the orbit, and likewise in the plot colored with time, you can see that you're finding your way onto the orbit from somewhere fairly far away. So that's good. So a fairly simple way you can avoid this issue of not having a good starting point. One thing I noticed though was that if you plot your Q measure, it doesn't fall away to machine precision. And the way you should read this is, because I'm doing this switching, that's why these curves it looks so kind of broad, and it kind of maps out this big wide region. So the top of this area is where the gain is 0, and the bottom is where the gain is large. But it's not going to 0, and I wondered why. And it turns out that the reason it's not going to 0 is because of the period that I'm using isn't good enough. So I started off using a period coming from the Newton GMRS convergence of this solution, and it turns out that this number is not converged all the way to machine precision, even though the tolerance for the Newton GMRS method is quite high, because the tolerance essentially isn't set for the period, it's set for the full state vector. So I came up with another method to, on the fly, update the delay period capital T. So I have some reduced measure of the size of the delay term. I don't want to go into too much detail on this. I basically do a quadratic fit. I find the minimum of the residual using a quadratic fit around time steps, and in that way I keep the number of time steps in the delay period fixed, but I update the size of the time step based on trying to find a minimum of this residual measure. And obviously I kind of restrict myself so that I don't end up wandering too far from my target orbit. So here is the result of doing my adaptive method, and you can see it's about 10 to the minus 3 difference. So that's the reason why the Q measure doesn't vanish completely, because I didn't have a good enough estimate of the period when I started. So here is now the green curve showing the convergence with the updating of the period. That's now going down to more acceptable levels. And moreover, now you can start with a much kind of weaker guess at what that period was. So I started this with 36.5 and was able to converge down to this number. Okay, so for the periodic orbit case, it's a little more sensitive to a few things. One, the starting point, and two, the period. So we need to do a bit of work there, but we also will need to do a bit more work addressing this odd number limitation. So if you look at the collection of UPOs that you typically get from a recurrent flow analysis, so we have a kind of catalog of those solutions that most of them do have a real, some purely real flow K exponent. So they're going to satisfy in general, I think, this odd number limitation. So we need to come up with some ways which don't involve symmetries, because obviously at high Reynolds number you're typically going to have all of the symmetries broken. So we will need some other way to kind of get around this odd number limitation. So we're currently working on a few ideas how we might get around this issue. So this is what Tissi has been working on lately, is this method of Purgas and Purgas, this act and wait method, where you're switching the gain on and off, but you're doing it at a frequency which is less than the period of the periodic orbit, and in that way you can avoid the odd number limitation. So you can read more about that in the paper there. So that's kind of the future work. So that's basically my talk done. Thanks for your attention. So we've basically shown that this method can stabilize exact coherent structures, namely the laminar flow, traveling waves, up to relatively high Reynolds numbers with a fairly, I would argue, simple implementation. So another thing that we'll need to do is see how well this carries across to other flow geometries. So if we try it in a wall-bounded shear flow, for example, a pipe or a channel or a Couette flow type of configuration, see how if the results I've shown here can carry across. And also I've shown that you can stabilize periodic orbits in the Navier-Stokes equations using this approach. However, it does get a bit tricky in this high-dimensional system, and we may need sort of more sophisticated ways of setting up the problem. So with that, I'll finish. If you have any questions, I'll be happy to take them. And there's my website there for more details. Thanks.
Cool. Well, thank you. Thanks, Dan, for that talk. So as Dan mentioned, we do have some time for questions. If people want to just unmute themselves and ask, or you can put your hand up in the chat and we can call on you, whatever's easiest. Cool. while we wait for people to get their thoughts, I might ask oh, was that somebody?
I'm just trying to get the,
all right.
the chat. Comms mentioned, messaged me in private.
Can I just ask, Dan, so like this switching method, somehow it's surprising how well that works somehow to me. Like I'm just trying to get my head around it, so I haven't come across it before. But like, were you surprised that it worked so well, that it really pulled in the solution?
Yeah, particularly for that first traveling wave I showed. And obviously that's a function of that coherent structure having this nice unstable spectrum, which is purely complex. So it's like perfectly suited to the method. So in some sense, it's a bit of an outlier, I think, in that respect. So you shouldn't expect this just to kind of work on any old exact coherent structure in general. I don't think there will be the odd one which is very well suited for it, and for the rest, we'll need to come up with a better method to find it, whether it's using symmetries if your solution has any, or something like the acton weight that I mentioned at the end. But yeah, exactly. In general, it shouldn't be as effective as I've maybe made out it to be. I think the result from the linear stability analysis was quite helpful in sort of pointing the way as to how you would how you could go about this thing, and making sure that I was confident that what I was getting was reasonable.
Cool. This is my comment. Anyone from the audience have a question?
Everyone's tired. It's too late in the day there.
Yeah. Too late here and too early in the UK. Can I just ask, so, I mean, you mentioned it right at the end that like eventually maybe the next step would be applying it to a wall-bounded flow, but is that where you're going to take it, or are you still?
We have a code and we're sort of just working on making the changes. We're trying to do too many things at once at the moment. I think we're kind of we're trying to address this odd number problem and also get spun up with other flows. So watch this space.
Yeah, it's on your to-do list. Okay,
it's on the to-do list. Yeah, I mean, so I have quite a bit of experience working in the Kolmogorov flow case, so that was the obvious place for me to start working, because I knew far more about it than I do even playing Coet flow. So.
Oh, right. Okay. Yeah, it's just because how you introduced it with the plain Coet flow. I was wondering if it was going to loop back around.
Yeah, well, I thought that might be, I don't know, maybe more familiar to people, or kind of slightly more physically relevant. You can actually do an experiment of that flow configuration. I mean, you can do experiments of the Kolmogorov flow case, but it's not quite. The boundary conditions are a bit different than things obviously in the lab.
Cool. All right. Anyone last minute questions or comments? Yeah, it's about dinner time here, unfortunately, Dan. So.
Yeah, everyone's stomach's rumbling. I might go and have a second breakfast.
Oh yes, that'd be a good move, I think. All right. If there's no more questions, I might thank Dan again for his talk, and we'll see hopefully most of you next week for our final AFMS seminar for this semester. All right.
Another thing is, well, everyone will go into comms talk, won't they?
Yeah, they'll start moving off. Yeah, probably from now, I think. So, yeah, two talks.
Thanks, Dan.
Cool. Thanks for the opportunity to talk. That was great.
Thank you.